Relativity is about how things change when viewed from different points of view. In physics, we call a point of view a frame of reference, which is defined as a coordinate system relative to which motion is described or observed. An inertial frame of reference is a frame of reference that is not accelerating. In this type of frame of reference, the law of inertia holds, which means that an object at rest remains at rest, and an object moving with constant velocity continues to move at that same velocity unless acted upon by an outside force. Our studies of special relativity will mostly deal with this kind of frame of reference. The principle of relativity is a concept that dates back to Galileo in the 1600s. It says that all laws of physics are the same in all inertial frames. Einstein believed in this principle. Late in the 19th century, two of the most important ideas in physics were Maxwell's equations of electromagnetism and Newton's laws of motion. Maxwell's equations predict that light travels at a speed of c equal to 3 times 10 to the power of 8 meters per second in a vacuum, but they do not specify the frame of reference in which light has this speed. This was a contradiction with Newtonian mechanics, which states that velocities act like simple vectors. To see why there is a contradiction, pretend you are traveling at half the speed of light in the same direction as a beam of light. From your frame of reference, the beam of light will be traveling at half of c, or 1.5 times 10 to the power of 8 meters per second, but this contradicts Maxwell's statement, meaning that Maxwell's equations don't apply in your frame of reference. There are two ways to resolve this contradiction. The first way is to say that Maxwell's equations of electromagnetism are incomplete and the beam of light does travel at a different speed in your frame of reference, in this case, half of c. Einstein didn't like this option because it suggests that different rules of electromagnetism apply in different inertial frames of reference and therefore contradicting the principle of relativity which Einstein believed in. The second way to resolve the contradiction is to say that Newton is wrong and the beam of light actually travels at c from your frame of reference. Although this seems counterintuitive, Einstein said that this was the correct way to resolve the contradiction. This meant that Einstein would have to create a new theory to explain the phenomena to replace Newton's laws of motion. Einstein set out to do this by beginning with two postulates. Number one, the principle of relativity, which states that the laws of physics are the same in all inertial frames of reference. And number two, the speed of light principle, which states that there exists at least one inertial frame of reference from which the speed of light in a vacuum c is independent of the motion of the source of the light. These are the two postulates that Einstein used to develop the special theory of relativity, which this video talks about. Note that if the speed of light is constant in one inertial frame of reference as suggested by postulate 2, then it must be constant for all inertial frames of reference according to postulate 1, which says that the laws of physics are the same in all inertial frames of reference. This idea resulted in implications that revolutionized our understanding of space and time. An example of this is time dilation, which refers to the slowing down of time of a process that is moving relative to an observer when viewed from that observer's frame of reference. We're going to be discovering the extent to which time slows down using a thought experiment. But before that, I want to define what a light clock is. A light clock is a theoretical object that consists of two reflective surfaces, and these surfaces trap a pulse of light that travels up and then back down. If we define this distance as d, then we know that the time it takes for the light pulse to travel up and then down is equal to 2d by c, as c is the speed of light. Therefore, we can time different processes using this light clock. For the actual thought experiment, we're going to have a moving platform that is moving to the right at a speed of v, and we're going to have a light clock on that platform, and we're going to have an observer named Alex on the platform, and we're also going to have an observer named Bob who is on the ground looking at the platform. From the frame of reference of Alex, we know that the light clock will be at rest, so it will behave like normally. The light pulse will travel up and then back down. So the time period that it takes for the light pulse to travel up and down from the perspective of Alex will be delta Ts equal to 2d by c. But from the frame of reference of Bob, the light clock is actually going to move to the right along with the moving platform. So it's going to start from the left, it's going to get to the middle, and then it's going to end up at the right. So the path that the light pulse actually takes is that it's going to begin over here, and then it's going to take this diagonal path as the light clock travels to the right. And we can see that the distance of the path that this light pulse took for Bob is a lot larger than the distance of the path that Alex saw, which was just up and down. But according to our postulates, the speed of light is still c in Bob's frame of reference. This means that in Bob's frame of reference, the pulse of light travels a greater distance with the same speed, meaning that there must have been a greater time interval. Let's call this time interval delta Tm, and we know that delta Tm is greater than delta Ts. And we can actually figure out how much greater delta Tm is by considering the path that the light pulse takes from Bob's frame of reference. So this is the path that the light pulse takes, and let's draw the line to make it a triangle. Let's call this distance z, and by symmetry this is also z, and let's draw a perpendicular line down. We know the distance is d, since this distance is d, and we know that this length of the base is just v times delta Tm, because v is the speed of the platform and delta Tm is the time it takes for the platform to get from this position to this position. And we know from Pythagorean theorem that z squared is equal to d squared plus v delta Tm divided by 2 squared, because we're only concerned with this triangle. And we know that distance is equal to speed times time, and the light pulse traveled 2z, and the speed that it was traveling at is c, and the time it took was delta Tm. So therefore, z is equal to c delta Tm divided by 2. We now substitute the z into our first equation, move this term to the left, factor the delta Tm squared out, divide both sides by this term. On the right side, multiply the numerator and the denominator by 4. Square root both sides. On the right side, multiply the numerator and the denominator by 1 by c. Simplify the denominator. Substitute the 2d by c term with delta Ts. This is our time dilation equation. I'm going to write this as delta Ts times 1 divided by square root of 1 minus v squared by c squared. And this factor here is actually called the Lorentz factor. And it has a symbol of gamma, and it shows up very frequently in special relativity. Now, what this expression says is that the duration of a process as measured by an observer who is moving at a speed v relative to that process is equal to the duration of the process as measured by an observer who is at rest relative to that process times the Lorentz factor. Let's analyze this equation to see what happens when v takes on different values. When v is equal to 0, then we see that this term becomes 0, and we get 1 divided by 1 equal to 1, meaning that delta Tm is equal to delta Ts. When v is somewhere between 0 and c, then we see that this term becomes some value between 0 and 1, and 1 minus that value becomes some value between 0 and 1, and the square root of that value again becomes some value between 0 and 1, and this entire value just becomes 1 divided by some value between 0 and 1, giving you a value larger than 1. This means that delta Tm is equal to delta Ts times some value larger than 1, meaning that delta Tm is greater than delta Ts. What happens when v is equal to c? Then this term becomes 1, and we get 1 minus 1 is equal to 0, and we get 1 divided by 0, giving us an undefined case. The same thing happens when v is larger than c. This term becomes some value larger than 1, 1 minus that value is some negative value, and the square root of a negative value is not defined, again giving us an undefined case. What we see in this analysis is that a moving clock will run slower than a stationary clock relative to u. We also see that time dilation cannot be applied to processes moving at or faster than the speed of light. It actually turns out that the speed of light is the ultimate speed limit of our universe. What I have here is a graph between delta Tm by delta Ts and v by c. We see that as the speed of the process that we are observing, v, increases and approaches the speed of light c, v by c approaches the value of 1. And as this happens, the value of delta Tm by delta Ts approaches infinity, because this is an asymptote. And what this means is that as the speed of the process approaches the speed of light, the time dilation increases without limit. Because really what's increasing here is the delta Tm, because delta Ts stays the same. Delta Tm is the duration that the process that is moving with the speed v takes, meaning that it takes longer and longer without limit as it increases to infinity. This graph also tells us why we don't see time dilation in our daily lives. Because in our daily lives, we observe velocities that are usually around this area. And at this area, delta Tm by delta Ts is practically 1, meaning that time dilation effects are practically 0. So, we see that there is no correct way to time a process. From different frames of reference, we measure different time intervals on the light clock. Each of these different time intervals is a relativistic time, which is defined as time that is not absolute but changes depending on the observer's frame of reference. But there is a concept known as proper time, which is the duration of a process as measured from the frame of reference of an observer who is stationary relative to the process. So in our case, observer A or Alex measures the proper time of the light clock, which is known as delta Ts. Observer B or Bob measures another relativistic time of the light clock, delta Tm. Proper time is just the name of the concept. It is by no way the only correct way to measure time. Note that proper time is invariant, meaning that its value does not change when measured from different inertial frames of reference. This is because its meaning does not change. No matter what inertial frame of reference you are looking at the clock from, the proper time of the clock is still the duration that a stationary observer relative to the clock measures. The effect of time dilation was experimentally verified by the Hafley-Keating experiment in 1971. This experiment found that clocks moving at different speeds relative to the center of the Earth run slower relative to a clock recording proper time. The clock on the plane going west was effectively at rest in the system of clocks and kept track of the proper time that would be used to measure the time dilation effects of the other clocks. The clock on the Earth's surface, due to the Earth's rotation, had some speed relative to the Earth's center. The clock on the plane going east had the largest speed relative to the Earth's center. After accounting for the gravitational effects and the fact that none of the clocks were in a truly inertial frame of reference, scientists found that from the frame of reference of the Earth's center, the clock on Earth's surface ran slower than the clock on the westbound plane, and the clock on the eastbound plane ran even slower. The values of time dilation calculated were consistent with the predicted values, therefore experimentally verifying the existence of time dilation and the associated calculation. This is a sample problem on time dilation. Roger is traveling with a speed of 0.85 times the speed of light relative to Mia. Roger travels for 30 seconds as measured on his watch. Determine who measures the proper time for Roger's trip, Roger or Mia. Explain your answer. So proper time is the time measured by an observer who is stationary relative to whatever process we're analyzing. In this case, that process is Roger on his rocket ship on his trip. So obviously, Roger is going to be stationary relative to himself and the rocket ship and his overall trip. So Roger measures the proper time. B. Calculate the elapsed time on Mia's watch during this motion. Well, Mia is going to be observing Roger travel at 0.85 c relative to her, so the dilated time that she is going to be measuring is delta Tm equal to 1 by square root of 1 minus v squared by c squared times the proper time delta Ts. And if we just plug in the numbers for delta Ts is equal to 30 seconds because that is the proper time that we're given, and v equal to 0.85 c since that is the speed relative to Mia that Roger is traveling at, we get the answer of 57 seconds. Another intuitive idea that Einstein had to let go of to create special relativity is the idea that simultaneity is absolute between different frames of reference. Simultaneity is defined as the occurrence of two or more events at the same time. So the idea that Einstein had to let go of is that if two events happen at the same time in my frame of reference, then they must also happen at the same time in your frame of reference, no matter what speed you are traveling at relative to me. We will see that this is actually not the case. We're going to explore this idea with another thought experiment. We're again going to have Alex on his moving platform moving to the right at some speed v, and we're going to have Bob as the stationary observer. We're gonna have two lightning flashes strike at 1 and at 2. And these two flashes are gonna send pulses of light to Alex and also to Bob. It is worth to note that in this experiment, we're going to be looking at it from the frame of reference of a third person and not from the frame of reference of Alex nor Bob. With that being said, when the two lightning flashes strike, Alex and Bob are both going to be at the midpoint between 1 and 2. That means that this light pulse from 2 and this light pulse from 1 are going to hit Bob at the same time, so Bob is going to say that 2 and 1 happen at the same time, that they're simultaneous. But Alex is moving at some speed v to the right. So the light pulse from 2 is going to hit Alex before the light pulse from 1 because Alex is continuously getting closer to this light pulse and getting further from this light pulse. So Alex is going to say that 2 happens and then 1 happens, so they're not simultaneous. Note that this implication is a result from the fact that these two pulses of light have the same speed, which is the fastest speed that information can be transmitted in our universe, the speed of light. It turns out that this idea that events that are simultaneous in one frame of reference are not necessarily simultaneous in another is key to solving some supposed paradoxes that show up in special relativity. Like how our perception of time differs between different frames of reference, our perception of distance also changes. This effect is called length contraction, which is the compression of the distance between 2 points that are moving with constant velocity relative to an observer from that observer's inertial frame of reference. Like how we have proper time, we also have proper length, which is the distance between 2 points that are measured by an observer who is stationary relative to the 2 points. Relativistic length is the distance between 2 points as measured by an observer who is moving relative to the 2 points. We're going to use a thought experiment to derive length contraction. Again, we're going to have Alex on his moving platform moving at some speed v to the right, and we're going to have him move from point 1 to point 2. And Bob again is going to be a stationary observer. We know that Alex is going to be measuring delta TS or proper time for his trip from 1 to 2, and Bob is going to be measuring delta TM for Alex's trip from 1 to 2. The distance between 1 and 2 as measured by Bob is going to be LS or proper length because Bob is at rest relative to the points 1 and 2, and the distance between 1 and 2 as measured by Alex is going to be LM or relativistic length because Alex is moving relative to points 1 and 2. Now we're going to use the equation speed times time is equal to distance. From Bob's frame of reference, the speed that Alex is traveling at times the relativistic time is equal to the proper distance. From Alex's frame of reference, the speed times the proper time is equal to the relativistic distance. We know this relationship between relativistic time and proper time using time dilation. We can multiply both sides by v, we can replace this left side v delta tm with ls, and we can replace this v delta ts with lm. And we get this relationship between proper and relativistic length. We can rearrange this to get our length contraction equation. We can replace this factor with 1 by gamma, gamma being the Lorentz factor. This equation can now be read as relativistic length equal to proper length times 1 by gamma. This means that distance has an effect that is opposite with time. When relative speed increases, the relativistic time duration dilates while the relativistic length actually contracts. If we plot the graph between v by c and lm by ls like we did for time, we get a graph that is essentially the time graph flipped upside down. When the relative speed is small, the relativistic length is practically the same as the proper length. When the relative speed approaches the speed of light, the relativistic length approaches 0. This is a sample problem on length contraction. How we solve this is by using the length contraction formula. Spacecraft 1 moves at 0.755 times the speed of light relative to spacecraft 2. Spacecraft 1 measures the length of spacecraft 2 to be 475 meters. This is the relativistic length. Plug the relativistic length and the relative speed into our formula, then we solve for proper length, and we get 724 meters. Although many paradigms change with special relativity, the law of conservation of momentum still applies. However, we must make an adjustment to how we define momentum. Note that we're only concerned with the magnitudes of momentum, velocity, and force, so I will not be using vector notation. The problem with Newton's definition of momentum is that the only way to increase the momentum of an object is to increase its speed since mass doesn't change. When a consistent force is continuously applied to an object, its momentum must keep increasing. As the momentum increases, the object's speed must also increase until it is traveling faster than the speed of light, which is impossible according to special relativity. To solve this, we use relativistic momentum, which is the momentum of objects moving at speeds near the speed of light. As you can see, with this new definition of momentum can keep increasing without the speed ever reaching c. This is the expression for relativistic momentum. P equal to mv times the Lorentz factor, where m is the rest mass of the object and v is the speed of the object as measured from the frame of reference from which we're measuring momentum. This expression hints at the concept of relativistic mass, which is the mass of an object as measured by an observer moving with some speed v relative to the object. It is defined as the rest mass times the Lorentz factor. Rest mass, or proper mass, is the mass of an object as measured by an observer who is at rest relative to the object. Einstein applied the concept of relativistic mass to energy. He calculated the total energy of an object that has rest mass m and that is moving with some speed v relative to the observer. He calculated the total energy ET to be mc squared times the Lorentz factor, where c is the speed of light. The energy of an object at rest, so when v is equal to 0, is equal to mc squared, giving us the most famous physics equation of all time. This E-rest is called rest energy, the energy a massive object has when it is stationary relative to the observer. This energy is not a type of potential energy since it is not a result of interactions within some system. It is a property of the matter itself. This rest energy is invariant, meaning that a massive object will have the same rest energy even if it is moving. But a moving object will also have energy due to its motion on top of the rest energy. Therefore, the moving object's total energy will equal the object's energy due to motion plus its rest energy. This energy due to motion is called the relativistic kinetic energy EK and can be calculated as the total energy minus the rest energy. If we sub in the expressions for each term, we can now calculate an object's relativistic kinetic energy using the object's mass and its speed relative to the observer. Similarly to relativistic momentum, an object's relativistic kinetic energy can increase indefinitely without the object's speed ever reaching the speed of light. With Newton's definition of kinetic energy, half mv squared, the only way for kinetic energy to increase indefinitely is for the speed to increase past the speed of light. As I mentioned with special relativity's definition, kinetic energy can keep increasing without the speed ever reaching c. So you can keep doing work on the object and its kinetic energy will keep increasing due to the work energy theorem. But its speed will never reach the speed of light. You will need an infinite amount of energy to accelerate an object with non-zero mass to the speed of light. I want to revisit the concept of rest energy, which is the energy that any object with mass has when it is at rest. Rest energy of an object is equal to the object's rest mass times the speed of light squared. It turns out that rest mass can be converted to rest energy and vice versa. Therefore, rest energy and rest mass are equivalent. This notion unified our theories of mass and energy into a unified mass-energy theory. The conservation of energy principle is now the conservation of mass energy, which states that rest mass and energy are equivalent and that the sum of these two quantities after we mathematically convert them into the same units is conserved. This is how our sun and nuclear power generators generate their energy. Because of this c-squared term, they can convert tiny amounts of mass into large amounts of energy. The idea of relativity is not new. In fact, Einstein's first postulate is a restatement of Galileo's principle of relativity. What made special relativity special was that Einstein applied Galileo's principle of relativity to Maxwell's equations of electricity and magnetism, which said that light must travel at this specific speed c. Einstein's second postulate is based on Maxwell's equations. Galilean relativity obviously did not take into account Maxwell's equations. Einstein created special relativity by using the two postulates and letting go of some paradigms. Special relativity implied many things that were counterintuitive. 1. Space and time are no longer separate. Rather, they are interconnected into space-time. Time dilation and length contraction tell us that time and distance look different from different frames of reference. 2. Simultaneity is no longer absolute. And 3. Mass and energy are equivalent. A key difference between special relativity and classical mechanics is that special relativity uses Lorentz transformations to describe how the perception of space and time changes between different frames of reference, while Newtonian mechanics uses Galilean transformations. Lorentz transformations treat space and time as being interconnected, while Galilean transformations treat them as two separate entities. A lot of the equations presented in this video can be derived from Lorentz transformations. Thank you for watching the video.